Hello and welcome back. Welcome actually to problem or chapter, what is it, 30 and 1/2. I don't know where they come up with the 1/2 actually, because I think they call it like chapter 11 in binary or some weird thing. So it's kind of a weird chapter, but I think it's important to know how to convert binary to decimal, decimal to binary, and also binary to, octal to decimal and decimal to octal. And also hexadecimal comes in really handy also, especially in electronics. So I'm going to do a couple examples here for you and hopefully make it a little bit easier. What they do is they go over a couple examples and they show you how in here, I'll just tap on the screen, how to convert. But what they do is they kind of come up with kind of a hard way to do this, where they're converting 71 and they're finding the number in this list and then subtracting out. There's an easier way. There's a much easier way to do this, and it's actually how we do it in electronics. Let me erase this part here. And let me show you basically, first of all, how to convert binary to decimal, which is the easiest thing to do. If I just have a binary number, 1101, all you have to remember is what place each one of these numbers are. So this is the ones place, so 2 to the 0 is ones. This is the twos place, so I'm going to put a 2 there. This is the fours place, and this is the eighths place, 2 cubed. So all you got to do is you got to add up all the instances of a 1 that appear and use the number down here. But what they don't tell you in the explanation is what you're actually doing is multiplying. Multiply, 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 multiply. And in binary, they skip telling you to multiply because you're multiplying by a 1 or a 0. So you really don't have to multiply, do you? You just add up these numbers. But once you switch over to octal and hexadecimal, this multiplication business turns out to be very, very important. And I should also point out that this only has 4 digits here. 4 digits. So to make a whole byte of information, see if I can undo that. To make a whole byte of information, you need a total of 8 digits. So this is one whole byte, B-Y-T-E. By the way, 4, though, we do sometimes use 4 in electronics, and half of a byte is called a nibble, believe it or not. I can't remember how to spell it, but it's not the regular spelling of nibble either. But you might want to look that up. It's kind of a funny little term. At any rate, I'm going to convert this binary number to a base 10 number. So 8 times 1 is 8, 4 times 1 is 4, 2 times 1 is 0. I won't write that one down. 1 times 1 is 1. So 8 plus 4 plus 1 is the total of 13. So 13 base 10 is equal to a 1101 in base 2. Pretty simple. And that's how all of them go. You just have to write down the number in the base that you want. You have to write down this little encoder, decoder, and then you multiply them out, and then you add them all up, and that's how you get to the base 10. Let me show you another example. I'll show you an example in base 8. So the base 8 encoder, decoder, I guess is what you could call it, would be the ones place is 8 to the 0. Here, I'll just write down 8 to the 0. I didn't write down the 2 to the 0, 2 to the 1. I thought you could kind of follow me, but for the 8s, I think I will. So 8 to the 1, 8 to the 1's power, 1, 8 squared, and 8 cubed. 8 to the 0 is 1. 8 to the 1 is 8. 8 times 8 is 64. 8 times 8 times 8 is, it must be, I think it's 512. Like that. And then what you do, so this is the encoder decoder thing. That's just that's my own term. Don't quote me on that. That's not a real thing. That's just Mr. Aaron making stuff up again. But let's say I want to convert a number to, and let me erase this top part also so we don't get confused here. So that's the numbers that I used for the last problem. Let's say I want to convert the number 72 base 8 to some number base 10. So I take this and multiply. You can see why I didn't use a large number, because if I had a large number over here, now I have to multiply by 64. And I just don't want to do that. So 2 times 1 is 2. 7 times 8 is 56. You add those together and you end up with 58 base 10. Easy. You just take your base whatever number, either by base 2 or base 8, you multiply it by the encoder decoder thing, and then you add up your numbers and you come up with your base 10 number. Okay, so all that's fine and good, but what happens when you want to go the opposite direction? Let's see if we can find a, let's see, what was that? Is this a binary number here? Yeah, it looks like it's this one might be a good one to use here, though I don't think they give us the answer. Let's see if we can find one where they actually give us the answer. Okay, so I found this one that they did. They wanted to convert the number 63 right here to binary, and you can see where she's going through. It's like, well, okay, it's got a 32, so we subtract out a 32, and it's got a 16, so we're going to subtract out a 16, and then it's got a 8, so we're going to subtract out an 8. I don't know where they did that. Oh, it must have been here. And it makes it kind of confusing. So I'm going to show you a different way to do it. Not that that's not wrong. That is correct. That is a correct way to do it, but I got a much easier way for you to do it. So let's see. They want to convert 63 to binary. Okay, so to convert 63 to binary, what you do is you use modular division. See, I don't know why they didn't use that because we just went over modular division. So in order to convert 63, let's make sure I got that right. Yeah, 63 to, oops, 63 to binary. I'm going to take 63. Whoops, I think that's off the screen there, isn't it? Hold on a second here. 63. And divide it by 2. So 2 goes into 6 3 times. You put down your 6 down there, you subtract, and you end up with a 0. Carry down your 3, then 2 goes into 3 1 time, and you put down your 2, and you have, oops, not very good writing, a 1. So you have a remainder of 1. And since you're dividing by 2, your remainder is always going to be either a 0 or a 1. Okay, so we're always going to end up with a remainder of either 1 or 0. One second, let's make sure I'm... Okay, so let's make this a little neater here. I'm going to erase some of this stuff here and start over again. Then the next step I do is I want to keep track of these remainders, by the way, because what we're going to start doing is we're going to start filling in the binary number right over here. Okay, and the very first one goes in the very first place, so I'm going to go ahead and put a 1 there, and then I'm going to divide by 2 into 31 by 2. 31 divided by 2 is, it's going to go in there 15 times with a remainder of 1. So I'm going to put a 1 right over here. And then I'm going to divide 2 into 15. That's going to go 7 times with a remainder of 1. So I'm going to put another 1 right here. And then 2 goes into 7 3 times with a remainder of 1. So put a 1 right there. Then 2 goes into 3 1 time with a remainder of 1. I'm going to put another 1 right there. And then you got to go all the way until you get a 0, actually. So 2 goes into 1. Well, 2 doesn't go into 1, so I'm going to put a 0. 0 times 2 is 0. You subtract out, and you again have a remainder of 1. So I have a 1 right there. So a 31, or sorry, not 31, a 63 is equivalent of a 1, 1, 1, 1, 1, 1. Let's see, how many are there? 1, 2, 3, 4, 5, 6. And what do they get? They get the same thing. They have 1, 2, 3, 4, 5, 6 ones. But you can see that it's the way that they had to do it is a little bit convoluted. So I kind of like my way a little bit better. It's actually not my way. It's kind of actually a standard way of doing this. So there's 6 of them here. So to make it a byte of information, you need to add 2 more zeros. Now this system also works with base 8. Now in the videos, you may recall that they did this example, and I think we'll just do this example again. But they have a 10 to the base 8 is supposed to be equal to 72 to the base 8. Oh, sorry, 58 to the base 10 is supposed to be equal to 72 to the base 8. So let's see how we can convert those. Once again, to convert from base 8, the 72 is super easy. I think I showed you that earlier. I'm just going to focus on converting the 58 base 10 to a base 8. Okay, so to do that, you do the same exact process that we did before. We're going to convert a 58 to a base 8. Got a 58, so we want to go from 58 base 10, and we want to convert that to some number base 8. And all we got to do is use modular division. Oops, I think I'm off the screen there again, aren't I? Hold on one second. 58 base 8, and I want to go 58 base 10 to some number base 8. Okay, so 8 goes into 58 a total of 7 times. 7 times 8 is 56. You subtract that and you can end up with a 2. So it's remainder 2. And then we have the 8 goes into 7 business. 8 goes into 7 0 times. Oh, okay, great. Once I reach that 0, I know I'm done. I just need to solve this last problem. 8 times that is 0, subtracting, and you end up with a remainder of 7. So it looks like 27, but remember, this is the least significant bit. We're going to need to go down to the most significant bit, so that's this one here goes first. So it's going to be a 2 and then a 7. We write them just backwards. So the answer to this one is 72, and that is actually what they get in the book. So just remember, to convert a decimal to any other base, it's much, much easier to use the division process that I go over here. And then to convert base 8 or base 2 to base 10, you have to use that encoder-decoder business that I was talking about earlier, which is simpler. But this process here, converting from base 10 to any other base, is about the simplest way I think you can do it. Modular division, very, very handy. Well, I hope this helps. I'll see you guys next time.